Well, as introduced by Vincent, my name is Roberto Miat. I'm a marketing manager working for ARM. It's nice to see you very numerous here today. It's also nice to see some familiar faces in the audience. So this presentation will be about an exciting and innovative technology, GPU computing. So the rise and growth of mobile and embedded computing is bringing some interesting challenges to the table. Resolutions and screen sizes continue to increase. If you look at today, the 2013 trend for smartphone resolution, we are pushing towards Full HD and further. Tablet devices already beyond that. If we look at the digital television space, numbers are even more impressive. This year you're going to start seeing 4K television shipping. And the industry is already lining up a roadmap towards 8K resolutions. Now, numbers are pretty impressive. If you think about Full HD, one individual frame consists of around 2 million pixels. Ultra HD, 8K, is around 33 million pixels, 16 times more pixels to be processed. New and novel applications are also fueling the increased requirement for computational power. If you think about the mobile device, years ago it was only a tool to make and receive phone calls. Today, it is a social hub, it's the web browser, it's also a primary media consumer device. People watch the movies on it. It's also utilized to produce media. And most people use the mobile device to take photos. There's a very interesting technology area called computational photography, which is all about using software and algorithms to compensate and improve on the limitations of the device's features like the sensors and the lenses, for instance. Users, every time they come to upgrade the devices, and they do this at regular intervals, come to expect a significant improvement in quality and features. They expect a faster, more reactive and more fluid user interface. They expect an overall faster device, a better experience altogether. And in order to address this, there is a consistent requirement and growing requirement for additional computational power. Now, the growth of these trends bring interesting challenges and pressure for who has to design the processors that have to satisfy these computational requirements. And historically, solutions that were once reliable, like increasing operational frequency or laying down additional processing cores, are no longer sustainable in the long term due to limitations for energy consumptions and thermal budgets. It becomes therefore necessary to find ways to compute and process more energy efficiently. And there are some tools which are particularly good at this, in particular parallel computing and heterogeneous computing. So if we look at the history of computer architecture, it's easy to see how parallel computing has been pervasive throughout designs. If you look inside superscalar CPUs, the way that instructions can be executed, dispatched for execution in parallel, and concurrently run through the various pipelines in the processor. Instruction sets have been extended to support things like vector operations, single instruction, multiple data. Processor designers have laid down multiple cores. You can duplicate the ALUs and do SMP design. Dual-core, quad-core systems are pretty common in the mobile devices. And then, of course, we have heterogeneous computing, which is pretty much the de facto standard way in which system-on-chip designers bring together a variety of processors implementing different architectures together, tightly coupled in the same system. So you have a variety of processors available and a variety of type of parallelism, and this can be extracted in many ways. In some cases, the developers might get their hands dirty and write hand-optimized SIMD code. In some cases, the developer will utilize auto-vectorizing compilers, or perhaps place compiler directives in the code in order to tell the compiler where to try to parallelize. Or maybe the developer will utilize application APIs like POSIX threads, for instance, to explicitly say to express the parallelism in application. In other cases, you might choose to utilize accelerator APIs like OpenGL ES or OpenCL in order to drive accelerator and offload work to the accelerator. Either way, you have a variety of architectures and parallel computing methodologies. You have many ways in which these can be extracted. The key thing is to find the right parallelism and the right processor for the job to hand and use all this variety of processors together in the best way. Now, in all of this, there's been some very interesting evolution in processor design in the last few years, and one in particular I would like to focus on is GPU computing. If we look at the history of GPUs, a few years ago, with OpenCL and 1, for instance, GPUs were hardware accelerated with a fixed pipeline for graphics computation. OpenCL and 2 introduced programmable shaders that enable more flexibility in programming the accelerator, but it was again something to do specifically with graphics. More recent GPU designing extend this to general purpose computation through languages like OpenCL and Renderscript. Now it is possible now to write code of non-graphic nature and accelerate it onto the GPU. Now, the CPU and the GPU are fundamentally different architectures. This slide represents some generic points. It doesn't reflect any specific implementation. CPUs are designed for straight-line processing. They're designed for serial workloads, in some cases, task parallelism, whereby you might combine together different applications or different processors to run on different cores. They typically include a relatively small number of cores. Modern system on chips in the mobile space have 2 cores or perhaps quad cores. And they're good at handling a relatively small number of threads. If you have a same number of threads or less than the number of cores available, you're going to scale quite well. If you start having more threads than cores, then the operating system will start time slicing, and you're going to start having to deal with nice artifacts such as cache trashing. Pipelines are relatively short, but there is also a lot of logic which is specifically devoted to activities such as control, branch prediction, maintaining data locality with caches and so on. So if you have very branchy code, that's fine. The CPU is able to deal with it at low penalty. And of course, modern CPUs also introduce vector processing with single instruction multiple data. So if you look, for example, at the ARM Cortex-A15 processor, Neon, or any processor implementing the ARM v7 architecture, there's a Neon execution engine, 128-bit wide SIMD engine. In short, the CPU is a very powerful compute engine, but it is designed for general purpose computation. The GPU, on the other hand, is a totally different type of architecture. Historically, of course, it is designed for 2D and 3D graphics acceleration, and it continues to be very good at that. But now it is also extended to compute data parallel workloads of non-graphic nature. GPUs are good when you have a lot of parallel computation going on. If you have hundreds, perhaps thousands of threads progressing at the same time, that's what the GPU is good at. Typical GPU design implements a larger number of cores relative to CPUs. So if you look at desktop parts or server parts, here we're talking about, at the high end, 500, 1,000, 1,500 cores. In the mobile and embedded space, the numbers are a bit on a different level. We're talking perhaps 4, 8, 16, 32, depending on the architecture and model. And different architectures, of course, have different interpretation of what a core is. Pipelines tend to be relatively longer. GPUs tend to be not very good with interrupts, with context switches. They work well if they're left undisturbed to do the processing, and if this processing in particular doesn't have a lot of branching or control code. Because of the highly multi-threading nature, GPUs are very good for throughput processing, and they're very much latency tolerant. So as you can see, 2 different types of architectures with different characteristics. Some workloads will work well on one of them, some workloads on the other. But the key aspect is to be able to choose the right processor for the work to hand and to use them together as the 2 architectures complement each other. So the operating system will continue to run on your CPU, as you'd expect. And so will most of the application processing will continue to be on the CPU. The CPU will also be useful to accelerate a large amount of existing workloads. Let's not forget, it is still a very powerful compute engine. On a high-end system on chips, you're likely to have 2 or quad-core, SIMD-enabled, out-of-order execution enabled processors clocked at speeds approaching 2 gigahertz. But now that you have a GPU that you can offload work to, the developer has the possibility of shifting some of the heavy parallel computing onto it. And this can be done using modern programming APIs like OpenCL or Renderscript Compute if you're working with Android. The developer can choose to take heavy workloads and accelerate them on the CPU, or can choose to use the GPU as a peer processor to the CPU itself. So within frameworks like OpenCL and Renderscript, you can actually target the GPU and the CPU at the same time. The GPU is then going to become very useful to accelerate tasks like advanced image processing, to complement high-speed functionality and high-speed hardware pipeline, perhaps by enabling better programming of some intermediate stages or complementing the post-processing aspects of it. Video codecs might be accelerated and offloaded to the GPU, some particular blocks like motion vectors calculations or post-processing, and physics computation. And in this presentation, I will bring to you some hard examples of what our partners have been doing in this area. So to summarize the benefits of GPU computing, some use cases will benefit from sheer acceleration, sheer performance improvement. In other cases, your target might be to compute more efficiently and therefore maybe do more work in the same time budget or power budget. Overall, you're getting a platform level better use of resources by being able to load balance work across multiple processors. CPU resource can be spared by offloading a lot of computation onto the GPU. You might be able to use the CPU for additional tasks, or you might be able to scale it down by switching off cores or lowering the operational frequency. And two important aspects I'd like to highlight are portability and programmability. GPU computing is programmed using languages like OpenCL C or Script C, for instance. These languages are C99 based. That means that you can write your code and you can recompile it from multiple types of architectures. You still might want to have to optimize it for particular architecture, but the code is typically recompilable and will run on any target processor you have backend support for. And programmability. Software-based solutions are easier to modify and upgrade than hardware. Let's now look at the evolutionary timeline of GPU computing in the mobile and embedded space. So of course, there's been a lot of research and development going on in previous years to what we can see here. And these have culminated with products starting to appear in the market around 2012. The first landmark was when the first OpenCL Chronos conformant full profile implementation of OpenCL passed conformance tests and started featuring in mobile system on chip that silicon vendors were able to supply to OEMs. And this has happened with the Mali T604 MP4 processor featured in the Samsung Exynos 5 Dual system on chip. And the conformance was passed in August 2012. In a similar time frame, GPU compute-capable devices started shipping in the market. The Google Nexus 10 tablet, the Google Chromebook, the in-signal Andal development platforms, all real products with GPU computing capability, all based on the said Samsung system on chip on Mali T600 GPU technology. And a lot of these are on show today here on real demonstration, so you'll be able to have a look at them. Around 2012, again, OEMs, silicon vendors, the industry as a whole started taking real active interest around GPU computing, evaluating the performance, starting porting the software. There's also been a gradual rollout of GPU compute APIs in operating systems. So if you look at Android specifically, Renderscript Compute, Renderscript Compute was originally introduced in Honeycomb and actually prototyped since the times of Froyo, but it wasn't until Android 4.2 that the Renderscript Compute was extended to also target the GPU. And this was done with the Google Experience device for Android 4.2 later in 2012, which is what then became productized as the Nexus 10 device. So for the first time, an open operating system with a GPU compute API that developers can use on a real device. You can buy a Nexus 10 today on the internet, and you can start programming today Renderscript Compute on the Mali GPU. This brings us to 2013, this year. We are nearly halfway through this. A lot of exciting things have happened already, and a lot more exciting things are, I'm confident will happen later in the year around this. If we go back to the beginning of the year at the Consumer Electronics Show in Las Vegas, the first GPU compute mobile benchmarks were showcased on real silicon. And this was Kishonti Informatics showing off CL benchmark, a Renderscript Compute benchmark on, again, Mali-based silicon. First time this has happened in the industry. ISVs and OEMs have started porting and optimizing libraries for use cases and their use cases for GPU compute. There is evidence of that later in this presentation on some of our partners that we'll be presenting today. Key applications like computational photography, computer visions have been targeted, multimedia codecs like HEVC decode specifically, and so on. And as we progress into the future, 2014, 15 onwards, what we expect is, of course, a continuous improvement and maturation of GPU compute APIs, of heterogeneous computing APIs, and underlying hardware technologies, implementation of features from the heterogeneous system architecture, full system coherency, and of course, GPU computing to become a mainstream technology available on the majority, if not all, system-on-chip designs, and a tool in the hands of developers, of all developers, to be able to improve energy efficiency of the solutions. So in order to make GPU computing happen, it is critically important that a strong ecosystem is built around this. ARM is making a significant investment around this, around building a strong ecosystem for Mali GPU compute technology, and is doing so by engaging with leaders and experts across the industry, engaging with partners that have diverse expertises and skills, targeting a variety of markets and segments, and focusing on critical and important use cases for our end users. In the next few slides, I would like to highlight some of the results that our ecosystem partners were able to achieve using Mali GPU computing. This is just a selection of our partnership engagements. We are working with a large amount of partners, and I'll be able to talk to you in detail about this at the end of the presentation. So let's look at advanced image processing. So as we said, Renderscript Compute was introduced as an official GPU Compute API in Android since 4.2, and it's particularly useful to accelerate things like complex image filters. These results represent the work done by a company called Multicoreware. Liwa Zhang from Multicoreware will be presenting later today the details of this effort. Multicoreware implemented a library of Renderscript Compute functionality, and here's some of the speed up we've been able to see, running these on a stock off-the-shelf Nexus 10 device. So you can see the performance is pretty good and consistently better when deploying these workloads on the GPU. Here we're starting with the same Renderscript script C code in both cases. Some of it is, first we compile it using the standard LLVM path on the CPU on Android, and then we recompile that using the ARM compiler for Renderscript Compute and deploy that on the device itself. So it is an apples-to-apples comparison. Another example of effort by our ecosystem partner is from Synthesis Corporation. They're based in Japan, and they design codecs and image processing algorithms. They've taken two other algorithms, a superscaling algorithm and a high dynamic range algorithm, and optimized them using GPU compute. So the first one is utilizing Renderscript computation. And again, it's done on the Nexus 10 off-the-shelf device. So the C reference implementation was first optimized using Renderscript compute. And this time, Renderscript compute was run on the CPU. So here you have some offload to a different CPU than the one hosting the main application, and you have some Neon compiled code through Renderscript, LLVM. The best benefits were achieved when using CPU and GPU together. And this was when Synthesis offloaded Renderscript computation to the GPU and also utilized OpenCL to do the rendering. Performance was improved by nearly 4 times. For what concerns HDR, which is a very common computational photography algorithm, as you can see here, through a variety of samples tests, when using the CPU and GPU together, the average speedup was around 3 times than using the CPU only. To hammer the point a bit further, this is a list of tests which were carried out again on a Nexus 10 device, off-the-shelf device that you can just buy from the internet. These tests are sourced, you can access them, they come from the Android open source project repository. Again, they've been compiled using Renderscript on CPU and GPU. And as you can see, we have a large variety of tests like vignetting, fisheye, grayscale, all very compute-intensive computational photography algorithms, and all of them perform much better, regularly better on the GPU compared than running them on the CPU. So you get some acceleration, but of course, whilst you do this, the CPU is freed up to do other tasks. Another important use case is multimedia coding, and in particular, next generation of codecs, such as HEVC. Now, high-efficiency video coding is the latest video compression standard ratified by ITU January this year. It promises to improve the video quality as well as half the requirement for data compared to H.264. And it is designed to support higher resolutions such as 4K and 8K specifically. ARM is collaborating with a variety of codec vendors, many of them, in order to ensure that the industry has access to HEVC codecs as soon as possible throughout a variety of ARM platforms. And this is done through Neon acceleration as well as GPU compute acceleration. This is quite important because the standard has just been ratified. Today's system on chips do not have HEVC in hardware, and will be taking some time before HEVC hardware will appear in system on chips available to OEMs. And even when that happens, the first implementation might have some risk associated to the lack of content to validate the technology. So software flexibility might be a safer avenue. We're working with many partners, but one in particular, ETIAM, we're able to demonstrate on our Nexus 10 device how using GPU compute can improve HEVC decode. They were able to demonstrate 1080p decode in real time using GPU offload on this device already. And this demo is available for you to see. What they did is offloading motion compensation, inverse quantization, transforms, and deblocking onto the GPU while keeping the main part of the algorithm still on the CPU. This can reduce the CPU load of around 50% and at the same time improve speed of the coding of a similar rate, around 50% speed improvement. Another good example of application for GPU computing is physics. And this demonstration is also available for you to see here today. So physics is very commonly applicable to games, which are a popular application for mobile devices. So this is an in-house exercise. We have taken a physics engine and we're simulating a cloth, or flag if you wish. The cloth is represented by a rectangular shape. We subdivide that into 6,000 smaller squares. Each square will have 4 vertices. The vertices are connected by springs, and springs are property of retracting, of pulling and retracting. For each individual frame, we calculate all the forces applied to these vertices and springs. We also apply to it wind in one direction, and of course drag in the other direction from the material, the cloth, and gravity pushing the flag down. For each frame, we calculate the new position of each individual vertices after all forces have been calculated and applied, and then we render the new flag, frame after frame. So as you can see, there's a lot of computation required here, but by definition, this is very much a parallel problem, an embarrassing parallel problem, and therefore the GPU is much suited for this type of acceleration. So here's some of the results we were able to get and demonstrate here today for you. The standard, the reference implementation we started with was able to achieve 2.4 frames per second, running on one core, 6,000 particles or vertices. And this totally loaded the single core CPU that was utilized. We then multi-threaded this using p-threads. 4.7 frames per second, so good scaling. And across the 2 cores, an aggregate load of 95%. So you're still pretty much fully utilizing your processors. We then spent some time optimizing this using OpenCL and offloading all the computation onto the GPU. By doing so, we reduced the load on the CPU to 5%. So the dynamic voltage and frequency scaling is not enabled. So this is 5% of the overall computation capability. And we achieved 74 frames per second. So very big speed up in performance for this type of workload. Now, that's good if peak performance is what you're looking for. You might not require that. In fact, 74 frames per second is not going to improve your visual quality any more than 30 frames per second will do. So you might choose to either do more work with the computational capability you have, in which case, as you can see here in the image, we're doing 2 flags, for which we do 37 frames per second, doing twice the work, 12,000 vertices. Or you might choose to simply scale down your processing by lowering the frequency of the GPU. And here's one final use case, which is very important, computer vision. And this is also here on demonstration today. So computer vision entails the acquisition, processing, analysis of image data, and also the understanding of the content. So an example is, I want to take a photo with my camera. I've got my viewfinder on. Now, in real time, I'm detecting edges of elements, and then finding out where the faces are, detecting where the mouths are, the eyes are, and then only once every subject in the camera is smiling and had the eyes open, I trigger the shooter. And this clearly requires to be very fast and pretty much immediate in happening. So we looked at computer vision with much interest, and we did some internal studies. We've taken a face detection algorithm from the OpenCV library. We had to rewrite it to use OpenCL and run on the Mali T600 GPU. Performance was pretty good. The input data stays the same. There's a camera plugged into the device feeding 30 frames per second of VGA content. But the GPU was able to compute 6 times more work in the same time as the CPU would have been able to do. So 6 times improvement in performance, if you wish. We then instrumented the platform by so that we could measure the energy consumed by the CPU as well as the GPU and the overall system. and we tested our workloads. And what we did for consistency, we permuted the frequency of the GPU as well as the frequency of the CPU, so we could get a good matrix of results. And consistently throughout all of our tests, what we found is that when using the CPU and the GPU together, the system was more energy efficient than when using the CPU only to compute this workload. So as you can see here, lower is better, means less energy being consumed by the platform as a whole. This is on demonstration here as well today. So I hope I was able to share with you the enthusiasm I have for this technology. In conclusion, energy efficiency can be effectively delivered through heterogeneous computing. The important thing is to use the best processor for the task in hand, to balance workloads across all the available resources, and to use all the available processors well in concert. When you have heavy parallel computation to be dealing with, consider offloading this to the GPU. GPU computing is a powerful tool that applies very well to a vast variety of use cases. And as we've seen in this presentation today, good examples are computational photography, computer vision, multimedia codecs, and advanced image processing. And very importantly, the Mali ecosystem is making GPU computing a reality today. Thank you.